We are on the brink of a computing revolution, and it doesn't involve faster silicon chips. Our current artificial intelligence models require staggering, unsustainable amounts of electricity to operate. Yet the human brain does vastly more complex tasks on about 20 watts. I'm Anita, and welcome to a new video. To keep large language models running, tech giants are building data centers the size of small towns. We are hitting a physical limit with traditional electronics. We simply can't power them much further. But a new field called organoid intelligence offers a radical, almost science fiction alternative. What if we used living human brain tissue as the hardware for our next generation of computers? It sounds crazy, but this is already happening in labs around the world right now. Let's break down exactly how scientists are turning biology into functional hardware. An organoid is a tiny, three-dimensional mass of tissue grown from human stem cells. In this case, scientists grow clusters of thousands of active human neurons in a dish. To be clear, these are not miniature human brains floating in jars. They have no blood vessels, no sensory inputs, and they are usually smaller than a grain of sand. But just like the neurons in your head, they naturally want to form networks and communicate. The challenge was figuring out how to talk to them and how to get them to talk back. The solution is something called a microelectrode array, or MEA. It's essentially a flat computer chip covered in a microscopic grid of sensors. Scientists place the living organoid directly on top of this array, allowing the tissue to bond with the metal. This creates a direct two-way bridge between living biology and digital code. We can send electrical zaps in, and we can read the electrical sparks the cells fire back. In 2022, a company named Cortical Labs used this exact setup for their DishBrain project. They didn't just record the cells, they taught them how to play the classic video game Pong. They sent electrical signals representing the ball's location into the tissue. If the cells fired the right way to move the paddle and hit the ball, they received a predictable electrical pulse. If they missed the ball, they got a chaotic, unpredictable zap of noise instead. Because neural tissue naturally seeks order and avoids chaos, the cells actually learned to hit the ball. But Cortical Labs didn't stop at simple two-dimensional games like Pong. They have recently been feeding their biological systems data from the 1993 game Doom. These living cells are now learning to navigate complex, three-dimensional digital environments. This proves that organic neural networks can adapt to incredibly complex, changing data streams in real time. And they learn these tasks much faster and with far less data than traditional AI algorithms. This incredible efficiency is exactly why the industry is rushing to commercialize this technology. Another pioneer in this space is a Swiss company called FinalSpark, and they've taken a huge step forward. They have created the world's first remote access biocomputing platform for researchers. FinalSpark hosts an array of 16 living brain organoids, kept alive in specialized incubators. Scientists from anywhere in the world can log in and write code that runs directly on these living human cells. They are actively testing how long these organic processors can survive and function. With proper care and microfluidic life support, some of these neural clusters can compute for over 100 days. But as this technology scales up, it forces us to confront some deeply unsettling questions. Are we just building a better machine, or are we engineering something that can feel? Bioethicists are aggressively debating the moral status of these biological computers. If we use human brain tissue to learn and adapt, at what point does it become sentient? Could a biocomputer experience stress, or even a rudimentary form of pain when it fails a task? Currently, scientists agree that these isolated cell clusters lack the complexity for true consciousness. They are just acting on biological reflexes, like a muscle twitching when stimulated. But as researchers network millions of these cells together, that line may begin to blur. Biocomputing could completely solve the energy crisis facing the artificial intelligence industry today. We might soon replace massive, roaring server farms with quiet, living biological processors. The era of silicon dominance might be ending, making way for the era of wetware. What do you think? Are you ready for computers made of living biology? Please let me know in the comments, and don't forget to subscribe to the channel. Press the subscribe button and the bell icon so you never miss an incredible update. Thanks for watching.